unwild collective behavior in neuronal ensemble. So, let's start with a picture. So imagine that you are recording some neurons, or someone provides you some data, and the spiking activity of a bunch of cells. Of course, way more than 3. And so you got the spiking times, and the first step is to choose a time mean and binarize them. So in my case, I was focused on, you should keep in mind the time mean of, say, 20 milliseconds. So rather short, but not super short. And then you can binarize them and associate a binary variable sigma equal to 0, 1, depending if the neuron emitted or not spike in that particular time being. So doing so, for each temporal windows, you have a binary vector that I call a snapshot of the system configuration at a particular time. And so this is the rest of the way for treating the data. And so the big question is, now that I have this data, how I can make sense of that, so what I can do with that. In the literature, I've been proposed plenty of different approaches. Among those, there is one particular one has been proposed, not only but proposed by the other colleagues to an extent, and it is to disregard, neglect all the temporal details of the sequence of this binary vector sigma and just focus on the probability distribution of this sigma. So the idea is that if we look at the very long recording, then we can assume that somehow the vector sigma reached some stationary state that technically can be both equilibrium or non-equilibrium as a network, and that by characterizing its probability distribution, we are having a tool, we are building a tool for analyzing the line system. So of course, we are neglecting a lot of details, right? Of course, by neglecting the temporal behavior, we neglect all the information related to the dynamics of the system. However, the idea is that even so, by analyzing this object, we are still keeping something important, some important ingredient of the behavior of the system, and it's worth studying. The point is that describing this probability distribution is not an easy task. And the reason is that, as you all know, neurons are correlated, they are not independent. And so because they are correlated, I cannot characterize the neuron as a dependent model, so this P sigma does not factorize over the neuron. And so I have a dimensional problem, because if I have n neurons, let's say 100 neurons, then this object lies in the n-dimensional space, and is definitely too big to have an empirical characterization of this P sigma. And so, for this, the idea proposed by the dialectic coworkers is to use the maximum entropy principle, which suggests you to look for the probability distribution that is able to reproduce some empirical statistics of the data, like, for example, the mean of the single neuron average and the mean of the pairwise product. And among all the distribution that reproduce these statistics, you should take the one that maximizes that. You should take the one that has the largest. So if you do so, you end up with a model, functional form, with a model that takes the functional form of the well-known Ising model in the statistical physics literature, which is equipped with some native field hi that basically set the firing rate of each neuron and some interaction couplings Jij, so a network of couplings that put in interaction the different neurons. So this is just the functional form. Then you need to fix the parameter in order to reproduce the statistics of the data. And you can do this model learning. This is just model learning. Maximizing the likelihood. And you will obtain the set of parameters H star and Jij that actually reproduce the data. So for a small number of neurons, let's say 10 neurons, solving this problem is rather easy, and you can do it numerically. And if you do so, you obtain a model that actually is quite good in predicting the statistics of this binary vector sigma. So here in this plot, I show you the empirical frequency of each pattern observed in the data, so these are real data. And on the y-axis, the prediction of my model. And as you can see, the prediction lie close to the diagonal. In particular, those patterns that have a very large frequency are very well reproduced by the model. So, nice, we have a model, it's able to reproduce the statistics of the data, and this is the case for a small number of neurons. In the case of larger group of neurons, say 30 or more than that, solving the inference is not anymore easy, and you need specifically developed algorithms. And in the literature, I've been proposed a bunch of them, and I also have proposed my own that I'm going to use to do the inference throughout this talk. Okay, there's a lot of technical details here I don't want to enter, but if you have a question on that, I will be more than happy to discuss with you those technical issues. So, okay, now we have a model, we have an argument for inferring the parameters, and we should ask ourselves, is this a good model in order to characterize the behavior of neuron? And the first question that I might ask myself is it really able to characterize the collective behavior of neuron, to unwind the collective behavior of neuron? So in order to answer this question, I'm going to present you the results from the work that a few years ago in collaboration with Gaeta Boni and Francesco Battaglia and Neuroscience. So the idea here is to study the neuronal space of memory. And the idea is very simple, that if I learn something, I learn to solve whatever task, then it means that something has changed in the activity of my neuron from before the learning to after the learning. So I don't need to explain this to you. The underlying idea is that it's the hypothesis that connections among neurons are strengthened upon learning, so that neurons that encode the learning can be co-activated altogether. So those connections here are meant as a real connection, the biological connection between neurons. We ask ourselves if we can have like an evidence of this hypothesis for our functional connection, the functional connection of our model. So for that, we started by the data recorded by Adrian PH, and together with Francesco Battaglia. So in this experiment, you have a rat that is put in a Y-shaped maze, and it has to learn some food in order to find some food. And then you have recording during the sleep before the learning, before the task, and during the sleep after the task. So this gives me one experimental session composed by the recording during this pre-epoch. And among the pre-epoch, the neurons that were recorded were the same, so I can really follow the same neuron during the pre-epoch. This is one experimental session, and in that data set we had about 100 experimental sessions, so 100 days of recording. And the question is, first of all, if among the recorded, let's say the 40 recorded cells in this experimental session, any of the neurons did really participate, did take part in the learning. Because when you record, you choose some neuron at random, you cannot control them. And so the question is, it's not obvious that you're actually recording neurons that take part in the specific learning task. And if yes, how can we identify those neurons within the network of neurons that we record? So in that, we extended the work of Adrien and Francesco using our maximum ranking approach. And so the starting point was to infer a model for each epoch independently so that we obtain 3D independent network of couplings. And as you can see, the network of couplings looks rather similar among the different epochs, especially between the two sleeping sessions. You can see this similar structure is present there. Instead, during the awake, where the epoch where rat was learning, the couplings are different from that. And so the point here, the question is, do we see some change in this coupling structure that is related somehow to the network? Of course, we cannot analyze all the network in itself. We do not expect to observe this effect over all the network, but just on subset of neurons. And so, for that, we use a community detection technique in order to identify subset of neurons that shows this reinforcement of the couplings of our functional couplings in the rest. So this is an example for this particular experimental session. You see that we identified this group of 7 neurons that were not interacting before the learning, that became strongly interacting after the learning, and the change in interactions in the strengthen is kind of correlated to what happened during the task. So we were, in this particular session, we were able to identify this group. We were not able to identify such groups in all experimental sessions. This is expected because probably we were not recording neurons that they took part in the learning in all experimental sessions, but we have several examples of this. And so what I want you to retain from this is that, yes, the model, my maximum entropy model, was able to characterize the collective behavior of the neurons, that some neurons, group subset of cells, were starting interacting strongly with each other. And in particular, this collective behavior, the model was able to also identify the change in the collective behavior. And so the answer to my question is yes, maximum entropy model can be used to study collective behavior in neural ensemble. Do you have questions? Yeah.
I have a quick one before
Yeah.
to take a break. So I'm wondering about estimation noise and how that plays into your procedure for matching the stability of connections across sessions, especially in the awake versus sleep, where the state of the system is very different and the marginal statistics are very different.
So it's rather easy to estimate the error of the inferred couplings because you just need to, it's a convex problem, so you just need to take the secondary derivative of the likelihood, so you have an estimation of the error. And so you can really be sure that the change that we observe here are significant. And indeed they are. So it's here the couplings are 0, and the error is rather small compared to the change from here to here, before learning and after.
So do you do a pairwise element by element significance test using that metric, or how does?
That's, yeah, you can do that. Or you can do something more elaborate for taking into account all the couplings between the neurons. It's a covariance function, so you can do sandwiches. Okay, let's move on. So when I was constructing the model, I asked the model to be able to reproduce the statistics of the singular activity and the pairwise product. However, I was kind of free to choose as different observable to observe different statistics. And so the question is, are these pairwise correlation always the good choice, the statistics, always the good statistics to impose in order to obtain a good model of my data? So to answer this question, to give you an example, I will show you the results from the work that had been done by a very talented student, Tangan Yan, that worked with me a few years ago. So in this work, we analyzed 2 data sets from the temporal cortex of a human patient. And we had data from an awake state and also data from a sleeping state, in particular a slower sleep state. And for that, we applied our pairwise maximum entropy model through the 2 data sets independently. And then we asked if this is a good model in order to characterize the data. So, in order to test for this, what I will do is that I will test if the model is able to predict the probability distribution of what I like to call the magnetization in a statistical physics perspective. This is nothing as the number of active neurons in the same time, so the population activity. And so the question is my model able to reproduce the statistics? And if you look for the awake data, it's indeed that the model reproduces the empirical statistics, the empirical distribution very, very well. However, for the sleeping data, the model failed. You can see the model completely underestimated the probability of having a silence, so the neuron silence, and also underestimated the probability of having large number of neurons active in the same time period. So here we have about silent neurons in this data set. And so, from a neuroscience point of view, this is rather easy to understand why. Because we know that during slow sleep, we have oscillation. And oscillation are meant to be like oscillation of the whole network. And so the kind of correlation that can be induced by this oscillation are not pairwise. They will extend over the whole network. And so this explains why a model that just imposes pairwise correlation, so where the interaction of pairwise cannot reproduce the statistics of this oscillation that are network-wide. So what's your question?
My question is about what do you call neurons here? I mean, are you recording single neurons?
Yeah, this was usually recording with temporal.
Right.
So I should have specified. Yes.
So I wondered to which extent these statements generalize as a function of the number of simultaneously recorded neurons. So there were some earlier results showing that in the 20 to 40 neurons limit, pairwise is fine, but if you go to larger networks, like larger observations, it's no longer the case. At least in our hands in the hippocampus, you see the second case in a wake rodent.
Yeah, it's a good point. So as we showed in the past, in particular the work by Gasper, that shows that when you start analyzing larger and larger data sets, in particular when you pass 1,800 cells, sometimes the pairwise model does not allow you to predict very well. So in that case, so you're right, in that case you probably need to start introducing some more constraint to the model. However, the point here is not only that here the model works fine. The point here is that in the awake state, the model works much better than the sleeping state. So I'm not saying that here the model is perfect. Probably if I had more neuron, I should change slightly the model, but the comparison is striking.
Could you just explain why these oscillations can be explained by pairwise correlations? So I would have thought you just need the eigenvector for various metrics with all positive entries, and that would explain.
The point is the nature. So it's the next point that you will understand that the nature of the collective behavior. So you can have collective behavior that arises because pairs of neurons interact, or you can have collective behavior that arises because some external stimulus like introduce oscillation. And so if you do an oscillation, if a network does an oscillation, you will observe kind of correlation that may extend over the whole network. Whereas in case of pairwise, you will have pairwise correlation. So the structure of the correlation is different. And in fact, what we propose is to work with the model introduced by and then extended by Gardella and Olivier, which is a kind of change of framework. It's still a maximum entropy model, but instead of imposing the correlation, here we are imposing the interaction between each neuron, sigma I, so the activity of each neuron, there you are, sorry, and the total magnetization of the rest of the network, meaning the total activity of all the other neurons. So technically, this is a kind of mean field model where each neuron feels an average, a mean field from the rest of the network. And so this model is constructed to reproduce this probability distribution exactly. However, we can test if it is able to produce other statistics of the data, like the pairwise correlation. And indeed, what we observe is that in the case of the awake, the model failed. It is not able to reproduce the pairwise correlation, whereas in the case of sleeping data, where you have this oscillation, this model can take into account the coordination of the whole network, and we are able to reproduce the correlation.
But this one is also a maximum entropy model.
Yeah, it's a maximum entropy that reproduces the mean activity and this object.
So could you not combine both of these statistics?
Yeah, you could. But part is you will obtain a very complicated model and probably start overfitting something. The class that this is
like like the bottom of the scale of linearly with the number of terms you would actually exponent, right? It doesn't grow quadratically. The numbers
No, it does not. It has one more special property. You can compute the partition function of this model exactly. You can, yeah, so it's very, very easy to do the inference of this model because you can numerically compute. It takes linear time in computing the partition function. It's not exponential time. And so it's very easy. That's also why you don't want it to use absolute pairwise relation, but once you use this nice property. So the take-home message here is that, first of all, that maximum entropy approach can characterize different type of collective behavior, so pairwise collective behavior or network-wise collective behavior, and practically also that yes, you need to choose carefully the kind of observer that you impose when constructing the model, and that should depend on the collective behavior that you observe or expect to have in the data. Okay, so when I introduced some reality into this station state idea, I told you we are neglecting all the temporal behavior, and by doing so, we are neglecting also all possible presence of some external stimuli. The external stimuli can be all the other neurons that are not recording if I'm working in the prefrontal cortex, for example, or some sensory stimulus if I'm working in a sensory cortex. And so the question arises kind of naturally, can we extend this framework to introduce stimulus or at least time? In order to show you how we can do this, at least for a particular case, I will present you the case of the retina. So I'm sure Olivier later on will tell a lot about stimulus processing in the retina. So for my talk, I'm going to use the retina as a black box that takes some stimulus in as an input and provide as an output a sequence of snapshot activity, so a sequence of state of my network. So what happens if, so in the experiment, you can play the video that you prefer. It can be synthetic video or naturalistic video, whatever, and record the activity of the network. So what happens if I apply the stationary state hypothesis that is the standard maximum entropy pairwise Ising model? So as you can imagine, if I play a different video, so if I stimulate the retina with a different video, the response of the neuron will be different. And in fact, here I'm comparing the correlation that you can measure when the retina has been stimulated by a white-mounted stimulus compared to that when the retina was stimulated with a moving object. So in this case, it was an elongated bar that performs some vertical random motion, so random motion in vertical direction. So those are two very different stimulus because this one has zero or almost zero spatial correlation, whereas this video has a very strong spatial correlation that extends widely in space because the bar is elongated. Right? And this is also why we observe very different correlations in the two data sets. And so, not surprisingly, if I apply the Ising model, what I will obtain is that the inferred couplings will be different from the two recordings. So yes, you can observe that there are some couplings that are kind of close to the diagram, meaning that they are similar in case, but also there are a lot of couplings that are zero for the white noise, the checkerboard, and non-zero for the moving object. This is expected because the white noise has zero correlation, spatial correlation, where the moving object can correlate very distant neuron, and this correlation will translate in the couplings. And so the question is, we are kind of unsatisfied from this. Can we do better? Can we introduce and take into account the effect of the stimulus? So from a physics perspective, the idea for doing so is to mimic what is known as a stochastic path in the statistical physics community. What's a stochastic path? It's very simple. You have the volume with some interacting particles and a piston that has its own proper dynamics. And the idea is that the dynamics of the piston is very slow compared to the dynamics of the particle, so that you can imagine to discretize time and assume that for each position of the piston, the system reaches equilibrium, or at least a stationary state, and you can describe it as a collection of equilibrium phase or stationary state. So, if I translate this for the neural case, what I will do is that instead of having just one Ising model, I will have a collection of Ising models, one for each time being. And in this Ising model, you will see that the magnetic field allow them to have a temporal dependence that allow me to take into account the effect of the time-varying stimulus. However, my interaction couplings J and J are constant in time because they are thought to reproduce some properties of the functional properties of my retinal application. And so now I can try to see if this model can solve this issue here. But first I need some good data in order to infer this model, and this is where working on the retina simplify our life, is the fact that in the retina you can replay the very same stimulus as many times as you like. And so this is what I do here. We were repeating the very exact same video multiple times, and then I record the response of, in this case, one neuron over time, and then a line over trial. And of course, then I can take the average, and so I have the behavior of the mean activity of my neuron over time. And of course, I can do this for all the neurons, so this multilateral array recording allows me to record many neurons at the same time. And so I have many, let's say, 30 neurons and recording over time. And so I can construct the maximum entropy model that reproduces this average, so the average of each neuron activity in each time being, plus the overall correlation between pair of neurons, so that I will have one parameter for each neuron in each time being and a network of pairwise couplings. Constant. So I can take this data and do the inference, and what I observe is that even if I use two stimuli in the data set in response to two stimuli that are very different in statistics, I obtain some couplings that are really similar for the two conditions. What you should notice here is that I actually have a lot of quant here close to zero that you don't see in this.
Just a quick one. So how is this different from the stimulus-dependent Ising model of Gasper?
This is the time-dependent maximum model of Gasper. What we are doing here is kind of focusing it, instead of working on all the neurons recorded in the retina, we are focusing on one population of all cells of the same type. So in this case is off cell and off alpha cell and on alpha cell.
Okay, but both of them have stimulus dependence only in the positive covariance.
There is no actual stimulus, yeah.
Yeah, whatever you want to call your dependence axis.
Yeah, exactly. And so the first take home message here is that with this approach that I call adiabatic process hypothesis, yeah, this is the paper for Gasper. And is able this time-dependent Ising model or adiabatic process Ising model is able to disentangle the intrinsic interaction into network effect that arises thanks to this network of couplings that is proper to the retina because it's robust across stimuli, and is entangled them from extrinsic correlation that has been induced by the stimulus that can provide correlated into the same neuron. Lastly, as you can notice that now we have couplings that are all positive, either zero or positive. And in fact, in the retina, I can measure the distance between, the physical distance between neurons. And what I observe is that only nearby cell have a strong coupling, so the rest is zero. And in fact, I can construct a lattice where I put one retinal cell for each in their position. So these are the physical position of the of alpha cell in the retinal network, and I can draw a line if the coupling is bigger than a threshold that was kind of obviously here. And you can see that I'm constructing a near lattice with somehow triangular lattice. Of course, there are some missing cells here. In these recordings, you cannot record all the cells you miss. Okay. And so this is nicely built up a kind of model that resemble now very closely those that people study in statistical physics, because you have this interesting network interaction and network effect. So because of this, by knowing what can happen in this kind of model from statistical physics, the question is, okay, we have nearest neighbor interaction. Now we know that nearest neighbor interaction can generate very long-range collective behavior, so very long-range correlation. And so the question is, do this collective behavior extend widely in space and potentially well beyond the network size that they can analyze, they can record experimentally? And so, of course, I cannot answer this question by just looking at my data, because I will need much larger system size in order to see how widely this collective behavior extends in space. And the reason is that right now we can record a much larger population and much larger retinal patches. The problem is that we cannot record them synchronously. So typically you need to record them in different patches at the same time. And so in order to solve this issue, I used a model that we developed in this paper. So I will not enter in the technical details, but just want to tell you that we use populace in order to construct a kind of very big network. So these were 400 neurons, synthetic neurons, and we put some interaction in order to respect what we observe in real experiment. So what's the idea is that if I take a small patch here, its property will recall those immediate those that I observe in the real retinal experiment. And so the question is now that I have this large model, I can study the collective behavior and see how far they extend. So in order to do so, what I do is I study the synchrony that I define as the fluctuation of my magnetization or the fluctuation of the total population activity. So if neurons tend to synchronize over a large spatial scale, it means that this quantity will have very large fluctuation in a lot of times more or very large. And actually this is a variance of the sum, so you can develop it as the group-wise sum over all the group-wise chloride. This is just simple mathematics. And so the question is how this object grows with the system size. And what I do for measure this is that I'm not looking, I'm looking at many systems of, so I construct many systems of many different sizes from this, and then I compute the synchrony, and I plot it here as a function of the number of neurons in my patch, or as the radius of my patch, which will be the square, going as the square root of the number of neurons. And what you can observe is that synchrony grows, but then looks like saturated. So the question is if this synchrony does actually saturate or keep increasing. It's a very interesting question, but I cannot answer it here because this is a very synthetic and simple one. What is interesting is that this saturation, if any, it happens well up beyond the typical experimental size that you can record from. And so, if any, the situation happens well beyond experimental size, and this is telling me that if I want to study collective behavior in this network, I should always take care and be careful of the network size that I'm actually analyzing. I would like to stress that compared to previous results in the literature, I'm not taking the patch and considering more and more cells within the same patch, but I'm taking a patch that gets larger and larger. Okay, this is just the summary of what I explained to you today. And okay, we asked a bunch of questions about the maximum entropy principle, and I'll try to give you some of my answer to this question. So before concluding, just a general comment on maximum entropy. So compared to nowadays machine learning techniques, maximum entropy is not as efficient as other techniques that we see, for example, yesterday, right? So this is both in efficiency, flexibility, and also learning the model sometimes is very hard compared to more useful other model in machine learning. And so the question is, why should we keep using this maximum entropy models if nowadays we are so powerful technique? And in my opinion, the answer is that we can benefit from the link with statistical physics. In particular, all the things that we know from statistical physics can now be applied on the inferred model to study the properties of the inferred model. First of all, because we can understand the parameters of my inferred model. This is something that's usually very hard in modern machine learning, whereas in the case of maximum entropy, I know what the magnetic field is, I know what the coupling is, and in particular I know their effect of a change of the couplings in the network and so on. Plus, we can also use, and we proposed in the literature to use really the tool proper of statistical physics in order to study the inferred model and so to analyze some properties on the underlying system. Imagine like criticality, nowadays Gallup is working on normalization group and other tools. Okay, so with that, I'm done. I'd like to thank the students that worked with me, and they did all the works, and some of my colleagues, in particular Olivier Thierry Morin, Stéphane Denis, and also Neuroscience, which is what I had the first result that I showed you, and of course, the fundings and you for your attention.
So we have time for a couple of questions. This is a question or an argument, but I'll try to phrase this as a question. So, I sort of kind of want to probe the last discussion point that should we be using these methods, and in particular, this question about whether we can understand and interpret their parameters. This is very similar to the question I asked yesterday. We know that in a neural network, we don't have symmetric pairwise interactions. Right? And so even though we can understand these things from a physical point of view, because in those situations we do have pairwise symmetric interactions from Hamiltonian to the right. Here, they don't match the way that the system actually interacts. And so what does it mean to be able to understand and interpret that? Shouldn't we actually try to find a representation of the interactions that do match the causal physical elements of the neural circuit, and then understand that?
I think that this depends a lot on the system that you are analyzing. So for example, if you are working on the retina, then focusing on rational cells of the same type. So okay, you are missing some of the cells. If here probably there's a cell there as well. However, you are under good reconstruction of the neural network. In this case, those cells are interacting by a gap junction, which are kind of symmetrical, and it seems that the maximum entropy model, they reproduce it quite well with statistics. So indeed there is a strong link. And so understanding the parameter can be useful.
But they also have, these are ganglion cells.
Yeah.
Yeah, so they also have alkaline cells that are feeding into them, that are creating long-range correlations. They have,
those kind of
through, both flexible methods are creating additional.
In this case, not really. Those effects are included in the time-varying magnetic field because they are driven by the stimulus. The interaction really comes from gap junction. And so in that case, there is a kind of close match between real connection and what I'm inferring. In the case of the cortex, instead the situation is completely different. But the situation is different, first of all, because we are encoding, say, 100 neurons, 1,000 neurons, 10,000 neurons if you are incredible experimental, in a region where you have millions of neurons. So of course, even being able to try to reconstruct physiological and physical couplings between the neuron is kind of not satisfying. You do not have the whole picture from the experiment.
And they will be asymmetric. And they will be asymmetric.
The real connection for sure are asymmetric because we know synaptic connection is asymmetric, but sometimes, for example, in my utilities here, if I have, yeah, this is the data from Adrian Perash. So here you have some cross correlation, and in this case they are pretty much symmetric. So it can happen. Why? Because probably those are just say 14 neurons, and they are maybe connecting, but maybe there are no direct connection between them. They are driven mostly by external input, and those can even drive up symmetric correction. So you cannot really go into the physiological properties here, so you have functional models, and in that case, this is what you have the best you can do, and the fact that you can interpret the parameters of those functional models might be useful.
Okay. Can I jump on this into the kind of workshop discussion period? I'm not going to talk about the retina because actually, in fact, Ulisse might be in the case where you actually have symmetric connection because of conversions, but let me ask a broader question. When you do models where you have interaction between neurons, do you really believe they correspond to serious connection between these neurons? In my experience, every time actually people, and I know we're going to say no, but I mean, every time people actually try to do that, look at the experiments and all that, I mean, we know the relation is like really far from clear, and I would actually go as far as saying, maybe pulling things in a very extreme direction, saying that, is that even what we're trying to do when we actually model things with interactions?
I'm not sure, but my question then is about what does it mean to say that the model ends up being interpretable?
Right.
I think that's the issue.
Yeah. Okay. But what I mean is that, you know, is that basically when you have that kind of model, is your dream goal to actually be able to interpret it in terms of true connections? Because for me, maybe that's actually not exactly right. Maybe you don't want to do that. Maybe there are more interesting things to do with these great models that you have.
But then the definition of interpretability needs to be thought about.
I'm here perspective.
What I meant is just that because I have some experience on this kind of model, I know what's going to happen if I slightly change one parameter compared with what happens if I change another one. In particular, to change the magnetic field with respect to the parameter. So really like functional understanding, like because I know this model, I know the behavior that this model can show, how the activity depends on the parameter and so on. Which is something that I do because I take benefit from, I don't know, 60 years, maybe 100 years of research on this kind of models that we do not have for recent machine learning.
Well, we do for dynamical systems, right? So not all of those have dynamical systems at their heart.
Yeah, of course. I'm not saying that those are the only models that provide this. I'm thinking more like deep learning things.
So, I think we should move on. So our next speaker is Conor Houghton. He's a reader in mathematical neuroscience in the computer science department at Bristol University. And his research is in information processing and coding in the brain, and mathematical and computational approaches to neuroscience. In particular, models of mood and movement and computational approaches to linguistics. And today we will talk about transfer entropy. It's very specific.
Thank you very much. Start off by thanking you for the invitation. I have to say, Edinburgh is my second favourite city in the world. Although I'm always somewhat, maybe in some ways pleased, but mostly alarmed to see the role. I'm Irish, and this Irishman here, Edinburgh, seems to play a large role in the sort of tourist accounts of Edinburgh. Really was a murderer, so it's great. Clearly, so far, what wasn't mentioned there is these days I've been working not so much on spike trains as I've started trying to understand how to interpret and analyze EEG signals with the aim of trying to understand the early crystals of language. And some of the talks yesterday, almost all the talks yesterday were just incredibly useful in helping my thinking about how we might do that, because certainly EEG, certainly the EEG approaches to EEG taken by cognitive folk it's a long way behind what people have achieved so far with the spike trains. So in the discussion of what we're discussing here, what I'm going to talk about very much falls into this picture here, even more so I think than Neil's talk. I'm interested, or what this talk is about, is taking data, all sorts of different sorts of data, spike trains from neurons, stimuli or behaviors, and then maybe population measures, field intentions, or whatever, and trying to infer from the data connections between them in as agnostic and in as model-free a way as is possible. So nothing that I'm going to say I think would never be as effective as what Neil was talking about, because it's completely as it were model-free. So what I'm going to talk about is estimating mutual information, and then at the end I'll just say a few bits about estimating transfer entropy. Now, the first part of this story is of course very familiar to you all. This is Shannon's entropy. We believe in Shannon's entropy because of the source coding theorem that shows that Shannon's entropy measures this sort of basic information. And then when we have more than one random variable, we have the joint distribution, we have the condition distributions, and we have the mutual information, which is the little bit in between. So what we want to do is to calculate this mutual information. And for spike trains, sorry, I usually try and remember to do this set of advert, because of course there's lots of other things that we can do, and you know, these days I'm often trying to sell more advanced methods to EEG folk, and you know, there are correlations and stuff, but we all believe deep down that, I'm seeing people from the machine learning community or outside the machine learning community, we all believe deep down that the mutual information is really the thing, the most important quantity. It's the true measure of the relationship between variables. But in practice, it can be very, very hard to estimate. Simply because it's very demanding of data, as we'll discuss. So, as was mentioned in the last talk, there's a sort of classical approach to this, where you take the spike train, you discretize it, you put it into bins, maybe with a set of bins, or 10 set of bins, or whatever. You split the bins into words, and then you do a lot of counting to calculate the probabilities. Because, you know, ultimately, you know, the reason that mutual information is hard to calculate, the reason entropy is hard to calculate is it involves the calculation of probabilities. If you're trying to do things in a model-free way, at some point, effectively, you're going to be counting occurrences of something and dividing them by something else, and that's something that requires lots of sampling. So, you know, this was developed by Gallic and co-workers in the late 90s, and famously, you know, they applied it to blowfish data, blowfly data. The blowfly has the current advantage that you can find in all the cells for a long time. You can repeat the same stimulus and get what you think is more or less the same response, because the blowfly isn't, like I have to say, people in the EEG machine, they're not distracted by daydreaming about what they're going to do when they finally get out of the machine. I don't think the blowfly ever gets out of the machine alive. Like our linguistic persons. So, you know, they're able to hold the cells for a long time, then they have tons and tons and tons of data, and so they can work out you know, entropy and mutual information and things like that. And again, we saw that in the last talk, you know, if you want to do long recordings, you want to hold cells, it's a challenge, unless it can be less of a challenge. But the point is that the classical approach to calculating entropy for spike trains, as you all know, is determined by undersampling. You know, if you're making words, you have lots and lots of words. People have, and again, we've seen from this, there's lots of things that you can do about that. Some model-free things, some things that involve models, some things that involve, as mentioned there in the last talk, maximum entry approaches. But the basic problem is that there is an sampling problem. There's also a sampling bias problem. When you're trying to sample data to estimate probabilities, you always end up with it's hard to, you have to do something extra to avoid ending up with a sampling bias. And again, there are lots and lots of clever approaches to that. But the point is that we're interested here, in not just extending the methods we have, discretization methods, whatever, so that we can have slightly longer words or slightly finer discretization. Then we want to be able to deal with the sort of data that we deal with these days, where there's hundreds and hundreds of neurons, where we want to do not just the mutual information between neuron and stimulus, but mutual information between neuron and neuron, mutual information between neurons and behaviors of stimulus that are continuous, and maybe unique, maybe are sort of one shot, but belong to some repertoire of behaviors. I work a bit with people who work on reaching experiments in cats, and the reaching is, each trajectory is all slightly different. You want mutual information between populations of neurons, or between individual neurons and populations. That's exactly the sort of stuff that fits into there. So you want an approach to this whole problem that isn't around being very clever about sampling problems, but rather being more simple-minded about thinking about what it is we're trying to calculate. So I'm going to sort of present to you an estimator for mutual information and by implication an estimator for transfer entropy that is rather simple. And in fact, it turns out when you try to do these calculations, you end up with something that looks like a KSG estimator, but the derivation of it is hoping to convince you has almost childlike simplicity. And the first sort of thing to note, or the background for what we're trying to do is metrics and distance functions. What happens when we start discretization, or what happens in a lot of approaches to estimating information in specific quantities, is you ignore the underlying geometry of the problem, because that's changing these days with the manifold approaches and so on. But I was very influenced by my mentor, Jonathan Victor, who always felt that we needed to take the sort of the geometry of neuroscience more seriously. And so this is a picture of Southbridge near here. So if we imagine that we're standing here on Southbridge, and we want to go to famous music rock ornaments, which is just there, the distance, as the crow flies, just like that. But we all know that probably leads astray, and if we arrange to meet somebody there in a minute, we would be late because the proximity structure is actually much more complicated. And that's kind of the point, that proximity structures are not always the obvious ones. The notion of distance that's important for a problem is not always the notion of distance that derives, for example, from the coordinates. And so I'm trying to set up the idea that what we want to do is not necessarily to find coordinates or manifolds for spike trace, although again, there are sort of clever ways where you can make sure that the manifold, the coordinate respects the distance structure of the problem. The distance structures are complicated. Maybe what we need to do is to forget about coordinates and work with spaces where there aren't necessarily coordinate structures, to move away from estimating things on manifolds and work directly in vector space. So again, this is just noting the same thing. When we do a discretization approach to calculating mutual information, of course, when you do discretize, you're in sound mathematical area, on sound mathematical footing. If you take the infinite, the limit of an infinite amount of data and infinitely small bins, the discretization approach, first outlined by Guy and co-workers, is going to converge on the correct answer. There's no question about that. It is the procedure that it is an approximation to the true value, which converges to the true value of the limit, but it can do so rather slowly. And in between, it is implicitly giving you some notion of proximity on the space of spike trains, in this case just one spike train. So, if the spike is there, if you move it just a small bit, then you're taking the distance between the two spike trains is the same because you're discretizing them to the same word. If you move it just a little bit more, as happens here, you've gone onto a different word. And as far as the forward distance is concerned, these are two completely different objects. And the probability of getting that word is not telling you anything about the probability of getting that one. And it's as if this, it's as if you have a hanging distance, and this is as far away from that, so it would be if the spike was over there. So, in other words, the classical approach to estimating mutual information or other entropy-style quantities on spike trains, somehow we can think of as implicitly imposing some sort of proximity structure on the space of spike trains, but not in a useful way. And so it's ways to look at the data. So my feeling was always that we could, by treating spike trains as living in a metric space, we can come up with better estimators. And part of the reason for thinking that is that there are lots and lots of good metrics on the space of spike trains. And one of the most obvious ones, I guess, or the most common ones, is the Van Rossum metric in Edinburgh. I'm not sure if he was here when he invented it, but you do, what you do is you take a spike train, you kernelize it with some sort of exponential kernel, and then you map the spike train to a function, and then of course you embed it into the space of functions, and you induce onto the space of spike trains a metric induced from the metric of the space of functions. It could be an L2 metric, an L1 metric, or whatever. And you can worry an awful lot about what the appropriate metric for spike trains is, and that's a mistake. So lots of people come up with new metrics for spike trains, and you do that myself, but it really doesn't matter, whether the metric on the space of functions in this case is an L1 metric or an L2 metric or whatever, and there's this metric of Victor and Barbara and Thomas Croix says all his metrics, and you can come up with some sort of definition of what a good metric is, and what a good metric is that responses to the same stimulus or similar stimuluses should be similar, and responses to very different stimuli should be very different. And according to those definitions, it matters a little bit, or it matters maybe a lot, what a kernel is, and some sort of adaptive kernel. But the main point is that the problem of how to, what should we think of, what space should we think of spike trains as belonging to? The answer seems to be, I believe the answer would be, it belongs to a metric space, and you can get metrics that you believe will capture the information coding structure of spike trains. It's just basically something about allowing for a bit of noise or jitter or whatever. And what's true of, and I should say you can calculate these things rather fast. There's sort of NRN style algorithms. I mean, this makes it look like it's an n-squared procedure, but it doesn't have to be. And what's true of individual spike trains is equally true of populations. So you can come up with multi-unit versions of the Van Rossum metric, multi-unit versus the Victor-Borker metric, multi-unit versions of all the metrics. The space of spike trains and the space of population responses, they can all be thought of as living in metric spaces. So what are we trying to do? Well, as I said, we want to estimate mutual information from data on metric space. So we just want to take the formula of mutual information and we want to apply it on a metric space. The rule is that all we can really use is the idea that there's a notion of distance on the space of data, and obviously there has to also be a measure on the space of data because it has a probability distribution on it. That's necessary if you're going to be calculating information style functions. So those are the rules. We're going to calculate mutual information for data on a metric space. And there's sort of two ways you can go do this. As I said, what we're trying to do when you're calculating entropy quantities is calculating probability densities. And so if you're calculating probability densities, one of the obvious ways to do that is to start to use kernel density estimation. thinking about how you use kernel density estimation in cases where you don't actually have coordinates starts off being a little bit confusing. You know, you make kernels without coordinates, etc. You can do that, and funnily enough, it turns out to be identical to the approach we use here, which is basically a hypothetical in-enco approach. And then what that turns out to give you is a nearest neighbors style estimator. So the formula we end up with is very similar in spirit and pretty similar proper details to the KSG estimators. So what I'm sort of selling for myself for my version of this is the kind of almost childlike simplicity of the derivation. It comes everything back down to the essentials. It's very easy to see how you do it and how you generalize it. And then coming from that is the fact that unlike the KSG estimator, the derivation I present to you now exists only in metric spaces. So it exists in metric spaces. It doesn't make any assumptions about the underlying, the existence of, or the properties of an underlying coordinates structure for the space that data lives in. And then finally, the estimator that I'll show you now, it's very easy to, although I'm not going to go through that calculation, which is the way my hands are playing through, it's very easy to work out the bias, the sampling bias, and so that you can debias it. And weirdly enough, in the KSG approach, it is a nearest neighbor approach, and so it's a K nearest neighbor approach. You need a value of K, and so what I'm going to sell to you is that if you debias the estimator for the mutual information, that actually helps you fix the value of K as well. So that's the plan. So just to go to the derivation, this is a dartboard. Darts, for those of you not from this country, is a game people play in pubs here where they drink too much and then throw arrows at the board. This is a used dartboard. I'm sure, and this was a few years ago, I'm sure it's pretty £8.40 now, in huge inflation, including inflation, I imagine, in dartboard prices. But the point, anyway, is that this is the dartboard. People throw the darts on the dartboard. The rules of darts make some locations of the board more valuable than others. So people in particular typically want to throw the dart towards the 20 slot here, and in particular towards the little slot in there when you get 60. The punishment being, of course, that which goes to the 1, which is a very bad throw. And the problem that we're imagining is that we're trying to estimate the probability density for the board, which is, I guess, some sort of estimate of how valuable each location in the board is. So imagine that you want to calculate the probability distribution for the dart hitting particular bits of the board. I'm sorry, I forgot my close up here, so you can see there's lots of holes here, and then there's fewer holes here. Fewer holes here, because nobody wants to get a 12, and if they are getting a 12 and not throwing towards the triple 12, so they're getting holes there, but we need something that's a highly desirable point. So the probability that, so we mark out in region B, the probability that the dart lands in B. Sorry, I know this stuff, you know, but again, what I'm trying to show you is you know, so how simple-minded the derivation of this metric-based estimators is. So the probability that the dart lands in the region B is just given by the interval of the probability density over that region, and you know, the number of holes in that region we expect to be equal to the probability of the dart landing in that region by the total number of holes in the obvious way. And so if the mass function varies slowly, so p of x is a slowly varying function of position, well then this integral is just given by the value of probability at some point within B, doesn't matter much where, which is assuming it's slowly varying, multiplied by the volume of B. And so you know, this is the essence of a thing called Leonenko estimator. The number of holes that we observed in that bit of the dartboard with volume B is equal to the probability distribution that we're trying to calculate by the volume of the region, you know, multiplied by the total number of holes. And so that gives us an estimator for P of x. So P of x is you take some region, in your space. So you want the probability distribution at some value x0. So you take a region around x0, and you count the number of data points in that region, and then the probability is equal to the total number of data points multiplied by the volume of the little region, and that's multiplying the number of points in the little region. And so in this case here, we're estimating the probability here to be 4 over n times the volume of that little region. I didn't estimate n in some stage, I don't remember what it is, but n, of course, is the total number of data points. So that's fine. That's how you derive Grothendieck-Leonenko estimators. The assumption that goes into it is, as I said, the idea that the probability density is still varying. The problem, of course, is that we do need to know the volume of this region. And so at this point here, you say, well, working out volumes is pretty easy. You know the dimension of your area, you have some formula which you have to look up, which involves gamma functions, alarmingly, that gives you the volume of all and dimensions. But of course, that all relies on you having coordinates. And the idea here, the rules here, which of course doesn't quite apply to a dartboard, is that you have no manifolds, you only have a metric space, so you don't know the dimension of your space, or if your space doesn't necessarily have a dimension, or if it does have a dimension, you're not making use of that. So we need some other way of calculating the volume. And that certainly doesn't really work at group level, though. The point is, of course, that you always have a way of working out the volume on a space where you're defining a probability distribution, because probability density functions are densities, so they do provide you with a measure. So we can write down the volume of the region B as just being the amount of probability density it contains. And in a way, that's a much more relevant definition of the volume than something to do with the coordinates. So the coordinates, might be appropriate to the structure of the data, but it might not. We think of visual images, for example, if you just construct volume walls based on the vector of pixel values, that ball won't in any way have similar to one image, all the images that are similar to it, and not images that are different from it. So to make the proximity structure in space of images should be using a greater number of distances or something. So this seems to be intuitively this is the right measure of volume for working out volumes on the space of data where you have a metric. And so the volume then, to estimate volume, because of course we don't have access to the probability distribution, the volume of the region B will just be the number of holes in B divided by the total number of holes. But of course, what we've just done, so I actually go through this calculation now, so we have this little region here as before, and the volume of that little region there, where we're taking, the little region has four holes in it, 4 data points. The volume is basically given by this number 4. So at this point, let's just pause and say, in these methods, this is what we're going to use the metric for. So the application of the metric in these estimators is fairly light. So I did say before that when we were thinking about spike trains, the goodness of one metric over the other, well, there's not much between them. They all seem to do the job reasonably well and pretty much as well as each other. And if you invent a new metric, you can find a data set that shows that yours is the best. But they're all much of a muchness. But in this case here, we're going to use the metric for making the little regions, the little walls. They'll just be the k nearest points. And so that's a very mild use of the metric. You can probably get away with a similarity structure rather than a metric. So we're going to be talking about the nearest h points a lot, and that's what the metric is for. It's for this definition of nearest. So anyway, as many of you have guessed, if I'm going to work out the volume of the little region using the probability density, well, that will effectively trivializing the probability density. So if I put in if I estimate the volume B here by the number of points in B, and I'm also using that to estimate the probability density, then the probability density will be constant. My estimated probability density will be constant. And so if you work out the entropy, you get 0. And that represents the fact that the entropy is not well defined. As you know, if you do a change in coordinates, or here a change in measure, you end up you can change the entropy, and you can always by just switching over, you can make it trivial. But you know, the mutual information is well defined. And the reason the mutual information is well defined is because it doesn't involve just one probability density. It involves, you know, at least two. So, you know, if this is the mutual information here, it's given by the entropy of the variable y minus the entropy of the variable y, which is the x, and that's part of the suite of similar such formulas. We switch around the x and y, etc. And so, when we're calculating the mutual information between two random variables, x and y, we do have, you know, at least two relevant probability distributions. And so the basic insight here, and as I said, hopefully I'll read you that this is very straightforward and simple. The basic insight is that if you're dealing with estimating mutual information on a metric space, you know, if you want to estimate the number of the probability distribution, all you have is the distribution of points and how close they are to each other, and you can use that to estimate the probability density. But you also need an estimate of the size of the ball, and to do that, well, the only thing you have to do that with, the only measure of volume you have, in the absence of any coordinates or any other sort of canonical volume measure, is the probability densities as well. But you have more than one probability density, and so you can use one, you basically trivialize one and use the other, estimate the other, and in doing that, that allows you to reasonably robustly estimate the mutual information. And so that's the idea. So I'm not going to go through the details. You can sort of imagine in your head what they might look like. You take each point, each of your data points, you expand a ball until it contains a fixed number of points, your h, which is what we're calling the k in the k nearest neighbor. And then you can do two things. You can sort of count according to one of the marginalized distributions, or the conditional distribution, or the joint distribution. There's lots of ways that you can count those points. You can count points according to their x value, or ignoring their x value, or whatever. So that gives you lots of different numbers of points inside balls, and that allows you to come up with an estimator for the mutual information. And so this is that estimator in the case where x is discrete. So this is when I first started working with Neuroscience, I used to work with Conor Houghton from the FAU on birdsong. And so, you know, a lot of the data sets that I used to work on had a bird singing, listening to a content-specific song. And in that case, then x would be the identity of the song, so that's kind of the easy variable, and then the hard variable would be the spike response, and so that's the variable that we regard as living in this metric space, and then the mutual information between the two, n is the total number of spike trains you have. Here I'm summing over the spike trains, and then I'm counting the number of spike trains corresponding to the same stimulus as yi in the ball, where the ball, I have a picture on the next page, I think you can do the precise order of these two slides now, but basically you choose one of the spiking responses, yi, you expand the ball around it. You do that because you have a metric, so you take, according to the metric, you use successive points until you have h spike trains in the ball, and then you count how many of them correspond to the same value of x as the point that you're interested in. So each of the points, of course, in the joint space will come with an x value and a y value. The y in this case being a spike train, x being the sum that's elicited that spike train, and so you take the ball of the nearest h spike trains to the particular spike train you're looking at the moment, and then you count how many of those come from the same stimulus as the point in the middle. So here's the vision that makes all this clear. So here we have two different, in the case of the zero-bit version, two different songs. We're interested in estimating the probability density at this point here, which will feed into the formula for the mutual information, and eventually giving you this formula here. So we're interested in estimating this quantity here. And so here the H is 8, so it's the bounded ball includes 8 spiking responses, and this ball lives in this space of spike trains, which is not to mention. here for illustrative papers is shown by dimension 2, expand the ball, and then I count how many red cells there are inside that ball, and that gives me the value of what in this version of the formula we call hash YIB, the number of YI type points in anything over all the points, and then that gives you this Bialenko estimator, which, as I said, is very similar. It's a K-neighbor formula, very similar to the KSG estimators. The advantage being that as I said, the determination is almost childlike in its simplicity. The formula is very simple, and it does allow, and I'm not going to go through this in detail, but it's pretty trivial because it's basically a learning problem. It does allow you to estimate the sampling bias. So these estimators have two kind of sources of error. One of them is related to the fact that you are imagining that P of X is trivial, is slowly varying inside the ball, in other words, that P of X is constant inside the ball. And obviously that fails as the ball gets bigger because the size of the ball gets bigger relative to the natural, variability length scale of P of X. And then secondly, of course, you need a reasonably large ball in order to effectively estimate this quantity by counting the points. So the bigger the ball, the more reliably you're estimating the probability density, probability mass it contains from the number of points in your data set, but the bigger the ball, the worse this approximation is. And so you're trying to do a compromise between the two. And it turns out that, as I said, you can actually work out the sampling bias for this. So, like all the database, counting estimates of mutual information is as a positive bias. But you can work out that positive bias. As I said, it becomes a simple curve problem if X and Y have nothing to do with each other. How many balls do you expect? What's the probability distribution for finding different numbers of red points inside the ball, based on combinatorics. And so you can estimate that bias, and then it turns out that if you maximize the bias-corrected estimator over H, that seems to give you a good value of H. And I don't know quite how you prove that. If you think about it, the intuition kind of makes sense, and it certainly seems to work on the picture-date versions that we've looked at. So that's the case where we have two variables. One is living in metric space, the other is discrete. And so that would be the case where you have spike trains or populations of spike trains against a discrete label for the stimuli. And the point is that it doesn't really matter if there are individual spike trains or population responses. We have metrics that can deal with all of those cases. It doesn't get harder just because you have more spikes. Work out the distances, the metric distance tensor between the data points, which we need, or the distance matrix between the data points, which we need. It's slightly more time consuming, but it's not, ruinously time consuming. It's a lot of the calculations that you might worry don't like the square of the number of spikes, that you go like the number of spikes, that's a lot of the number of spikes.
Does the bias not depend on the unknown joint distribution? You described something where you sort of calculate bias where it's more independent, but if they're not, does the bias change?
Yeah, so the bias that we correct for is the oversample being overestimated because of the
the sample size. But doesn't the expected size of that bias depend on what the joint is? That's what I'm confused with.
Why?
So in the extreme of the deterministic relationship, that will have a very different shape bias to that where they were actually dependent.
Yes, okay, so I need to make my statement more precise than that. There is an over-estimate of the mutual information because it estimates a non-zero value. Sorry, I'm going to speaker. It estimates a non-zero value in the case of the independent. That's what we can calculate. And removing that gives you a good value. Removing that and maximizing over H gives you a good value for the
so it's the bias in the case of independent.
Yes, actually, that's good. Two continuous variables. Good morning. Two continuous variables. it all follows through. Again, you've got two different probability distributions. You have one for one which is joint and one which is marginalized, and you can come up with the formula. And again, it's just a question of counting points. It turns out in this case you're counting points in future sections. So to work out the volume of a region, this little region here, so sorry, this is supposed to be one of the variables, this is the other variable, this little region here, the volume of that region, according to the a volume measure based on the marginalized, the probability distribution, the probability density you get for marginalizing the joint distribution in both directions, the independent one. The volume of the region in the middle is just the multiple of the volume of this region by the volume of this region. So you basically you expand out in one direction until you have 1, 2, 3, 4, 5, 6, 7. I use 8 again here until you have 8 points. You expand out in that direction until you have 8 points, and then you count the number. That gives you the volume of this little region in the middle, which would be 8 squared, divided by the total number of 8 points, and then you work out the number of points in that little region, which is the points related to the pairs, the XY pairs, and that gives you this number here, and then there's some other numbers, associated with the number of points, and the size of the kernel, and that gives you your information estimator for X, Y. Here's some predictive data, so using to calculate mutual information between two iterative parts of iterators, some noisy input, and some correlation in the inputs, etc. And I can vary that correlation to go from cases where the neurons have lots of mutual information to cases where the neurons have very little mutual information. And here I've estimated, the black line is the estimator I just presented using 2 seconds of data. This dotted line here is using the classical approach with 2,000 seconds of data, and then if I keep going, because data, I can get any amount of data. Eventually, I get what I would regard as probably the true value from the histogram, but it took 25,000 seconds of data, which is lots of the data we normally have. The estimator I've been presenting is very bad for when there's no mutual information, precisely because you're maximizing over H, and so there's a little bit of noise there, and you're maximizing over that noise, and that little bit of noise is what you get there, and you start to think ways of getting rid of that as well. But yeah, you don't bother, because for when there is actually mutual information, you can see it's rather good. So quickly, transfer entropy, in the last minute or two. The transfer entropy is a measure of causality. We know from analytical co-workers, it's basically the thing that gives you greater causality. So greater causality is transfer entropy for in some particular cases. And the transfer entropy is you have two variables, and you're looking at x goes to y. So you want to know the degree to which x is causing y. And what you do is you work out the mutual information of the current behavior of y based on the past of x, but conditioned on the past of y. So the transfer entropy is a conditional mutual information, and and that, of course, has very acute sampling problems because you have three random variables. It also tends to have very acute sampling problems if you want to do this over some extended period into the past. And so when people try and use transfer entropy for spy trains using bin approaches, they tend to have very large windows, filling windows, and then very short notions of what the past is. You can apply that in this case here, and the same sort of derivation goes through. You just end up with sort of three-way. There is a in the paper. This picture makes sense. At the moment, it's supposed to just illustrate the idea that all you do now is you have more of these bubbles, you do more intersections. You have to take into account the conditional. To work out the bias, you have to think a little bit more because you have to go a little bit further in the direction management suggesting I need to go overall in terms of working out the bias when you have not independent but conditionally independent distributions. But you can do all of that and come up with an estimator. We haven't tried this estimator with the data, but we tried the Einstein model with predictive data where we've taken 2 points of the Einstein model that are close together or far apart. And just very quickly, these are the results. Yep. The blue is our estimator. This is when when the points are very far apart, there's no mutual information, and these are some of the Kraskov estimators, or the KSG estimators. So here, the purple line is from histogram, which went up forever to get the purple line. Our estimator, after 100 or 1,000 samples, is already starting to do something right. The KSG estimators, for reasons like they don't fully understand, seem to sort of fail. And then again, when you see more mutual information, ours behave rather well. Their estimators don't do these strings. You really need billions and billions of data points for that to work. This looks like it's getting there, but if I could keep going, it's bullshit. Horizontal. So I'll stop there. Thank you very much.
We have time for a couple of questions.
So, if you need to calculate mutual information and you don't want to use a model, you want to use the parameters, I do encourage you to take this approach. It's a summary, even for cases where you have very complicated data, high dimensional data. Yep.
Sorry if I missed it, but is there a difference in scaling between quantum-based approach and density-based approach? Scaling to higher dimension, like many structures?
How do you mean by scaling?
I mean, as I understood, you talked about estimating mutual information between pairs of characters.
Yeah.
What if you want to estimate the mutual information between like a large population of humans versus
Yeah, so from a computational point of view, you need to work out the distance matrix, the matrix of distances between your data points, and that becomes a more difficult calculation as the number of points goes up. Absolutely. The quality estimator also improves somehow. Although these there is no dimension here, it feels that for more neurons, if you were trying to find some equivalent to embedding space, the number of dimensions is going up. And nearest neighbor estimators tend to behave better in higher dimensions, just because if you sample from balls in higher dimensions, you tend to end up on the periphery of the ball, so the relative volume on the outside of the ball is bigger. And so if you're not on the periphery somehow, it's a more even and less random event. So our experience is that for lower dimensions, when we do this on predictive data, for lower dimensions, the behavior of neighboring type estimators is not so dramatically better to histographic approaches as it is when you go to higher dimensions, but the histogram approaches entirely fail because your words goes up, but Canadians, neighbors, ours, KSG, etc., they tend to get better and better and better because they quite like being in higher dimensions. I think for these situations, English like this statement, but that's.
So would it be fair to say that proximity helps with high-dimensional?
Yeah, so I think if you want to calculate mutual information for high-dimensional vectors, either you do have coordinates using a nearest neighbors approach. So applying it to mutual information in the activity of middle layers of your neural networks or something, then this is probably good. Even though there is a sort of set of coordinates which it's associated with economic promotion distance, which is correct. This is still mutual roles. Because it exploits the distance. This point being there tells you something about property intensity, which histographic approaches need that. Yeah. Cool. Great.
This is a very good question because I don't actually work with mutual information very much, but are there ever really reliable model-based estimates of mutual information? I feel like most of the methods I see require to sort of avoid model-based estimates. Is that correct?
Oh, that's an interesting, again, I refer back to, we had model-based estimates yesterday that we're doing. And lots of people want to work out mutual information before functions. In the financial data world, in the EEG world, you have your trajectories. We want to work out mutual information between trajectories. And there's a whole industry of model-based approaches to that. We model those trajectories as progressive processes of some form or another, and then try and do some quasi-analytic, quasi-approximate approach to that distance. So yeah, there's different worlds where there's a lot of that going on. And, what I'd like to do is to compare our methods to some of those. But I haven't done. Okay. But I mean, if you have a model and the model is correct, then that's the best thing to do, right? I mean, this is if you've got no model, you've got no idea. You have some idea because you have a metric structure. But if that's the most efficient way for encapsulating your intuition for the problem or your knowledge of the problem, then I think this is good. If your knowledge of the problem gives you a good model, then that's that's going to make estimating your information better. It has to be.
Yeah, I guess it's my experience is mostly with neural data. I feel like even in the best of cases, there's just a huge amount of mismatch between the model and the
That's why I sort of felt the simplest approach possible. My complaint with my method is it's the simplest thing you can do because it just all you do is you have some points. You want to estimate probability density. You do it by counting the points. You want to estimate volume. You do it by counting the points. It just uses exactly what you have. Lying around. The stuff that you have to have, all problem exists at all.
Maybe. Well, I guess I just was wondering whether the experiments, which went by a quickly, actually address the question I was the sort of subtext of my previous which is so when you do have mutual information between two things, the bias that you calculate, assuming that you don't, I think is often an overestimate of the actualness. And so then you worry that you would overcorrect and underestimate. But what your experiments show that that's not happening.
Yeah, but I think there are experiments, right? I mean, I do experiments to show that our method works. It always does, And my experience is, it always seems to work really well.
Okay.
But, either I come up with artificial examples, or I work in cases where I have no parameters, so.
But at least in the artificial examples, it seemed like even when the actual mutual information was high, you weren't systematically underestimating that.
No, I've done lots of different versions of this, and it just seems to work really nicely. I mean, that's all I can say. But what I'm keen on is that people use Penanga for taking the problems and see it. Otherwise, I mean, oh, is it okay? I mean, I'd like people to use the formula. Maybe when they use it, it's going to turn out to be crappy. Maybe, I find the right sort of mathematical audience to present this, and they'll be able to do sort of calculations that you're outlining, or proof conversions, or whatever. I'm kind of in the middle case. I've done it on objective data. I've done it on other data, rats and mazes. I've done it to, I've done cases where you can compare the information with the transfer to be calculated my way with correct causality. It seems to work pretty well, but I'm acutely aware that when I say that to an audience, I can just take really pictures of it and say, well, of course, you're going to choose examples. That's good. So please use my formula and see if you can break it. If you can.
Okay. Thank you very much. We will continue at 1:15.